And maybe we'll talk more about that next time. But we can prove, of course, that this does converge, in fact, and not just for not for just some subset of special matrices that are nice and well-behaved for this to converge, but in fact for every stupid matrix that you can imagine, every single real or complex n by n matrix that converges. So there's no danger in that. So this conditional that you look at e to the tx, whether or not it's in G, that's totally a reasonable thing to check. Right. So now if that's the definition, right, if this is the definition of what a Lie algebra is, and I guess we can ask I mean, it's almost the same definition. Like, what would the definition of a tangent space be? Let me just talk about that for a second before I get sucked into the details here. So, what would the tangent space? Here's my sort of most basic idea about tangent spaces. A tangent space at a point, P, to a manifold M. All right. What that is it's just the set of really, you know, what you're doing. You're just saying. You can think of it this way. You're at the point P, right, and you look at gamma prime of 0 such that gamma is a mapping, let's say, from the reals for our convenience to the manifold, and gamma of 0 is the point P in question. And so that's what I would like envision as the tangent space. It's just this set of all possible tangents at that point. Now, I mean, so if I think about the tangent space at the identity to a Lie group G, a matrix Lie group G, right, then I don't need some kind of abstraction for tangent vectors. I can really just look at paths of matrices, and I can look at, say, gamma prime of 0 such that, you know, gamma is a mapping from the reals into the group G, and gamma of 0 is the point in question, I guess in this case I, right? And that would be it.
I'm still not seeing how they're the same.
Right. Fair enough. Why is it the same to look at, you know, you've got this group, right? It's some kind of, I don't know what it is exactly, but you got an identity in it, right? You got a curve, gamma, and then you've got these tangent vectors to the curve, right? I mean, I'm being very abstract here in my thinking, but you know, these something like this is the gamma prime of 0, right? Why on earth should that be equal to e to the tx for some x?
It's going to be x such that e to the tx is in G. The Lie algebra is not the exponential.
Oh, I'm sorry. Yeah, you're right. I have to say, I'm sorry. Okay, so that's not the right thing to look at either. Excuse me. So this should be x such that what? Thank you. E to the what? What do you say? E to the tx is an element of G. Thank you for keeping me honest. That would be very helpful. Not cool.
It must be painting. It's like, I mean, to get from like that one to this one, you just let, well, I guess it's close.
Yeah,
Like if your gamma is just e to the tx, then gamma prime of 0 is always going to be x.
So you're trying to game the system. You're like, well, why don't you just look at gamma of t is equal to e to the tx?
Yeah.
Then gamma prime of 0 will be, well, gamma prime of t will be x e to the tx by chain rule in evil homeworks that I assigned you in previous semesters, which now are coming to their fruition. Let's see here, gamma prime of 0, right, so, yeah.
That's to get from one side to another. But to show that like every such one is, yes,
Yeah. How do we know that every tangent vector can be realized as the exponential of some other vector? That must be true in order for this definition to make sense and this definition to make sense. Okay? I'm gonna set that aside as a technical question that we should think about. What I'm gonna do now is a little bit easier. I'm gonna actually find the Lie algebras of these groups. And it's actually not that hard to do it. So like, what is the Lie algebra, for example? Let's pick one that's a little bit. Actually, the most boring one is not entirely easy, because sometimes too little structure is too little structure. So let's look at ON. Let's think about ON. Let's try to find what's called little ON. Sorry. There, is that better? So what we're looking for, right, is what? Man, he approaches this a really different way. I'm not sure I can think his way yet. Let me go back to my way of thinking this way. So if we look at a curve, right? So I'm gonna stick with what I know for a moment. I'm gonna try to. There's got to be something really clever about that definition I don't appreciate yet. So the gamma, going from say the reals to the what? ON, right? And we want gamma of 0 to be the identity, all right? Let's find out what condition this imposes on gamma prime of 0. See, because if this is a curve in ON, right, that means that gamma of t transpose, right, times gamma of t is equal to what? It's in ON, right? That means it's on this group of matrices. It's on this surface, if you will, in the set GLNR. It's I don't know what the dimension of that surface is right off the top of my head, but you can figure it out, Z or I. And then what do you do? We should remember the advice of our previous book. What was it? Who told this to us? Was it Chern or Bott or Tu or who? I don't know. If in doubt, differentiate, yes. So we get what we get, gamma prime of t transpose times gamma of t plus, I regret my choice of notation here, gamma of t transpose gamma prime of t equals to a 0. Now that condition, of course, is going to be true along the whole curve, right? Like that's true along this whole curve if you want to think about that picture. But where it's most interesting is if we put t equals to 0, right? T equals to 0, then we've got what? We've got gamma prime of 0 transpose plus gamma prime of 0 is equal to 0. Since gamma of 0 is equal to identity, which is, by the way, the same as gamma of 0 transpose, right? So what we found then is that ON,
Anti-symmetric matrices.
exactly, it's just B in Rn by n such that B transpose is equal to minus B. Somehow, these exponentiate, right? If you believe this, if we take the exponential of something like this, right, we'll again satisfy, I mean, we can look at that, I guess. I mean, sure, why not? Let's think about this. If we have e to the b, right, and we do what? We transpose it. mean, I guess I should take it sometimes. Let's say I use S because T is I'm using for transpose, and then I do that times e to the bs. Barbara Streisand. Let's see here, and then what? We'd like to show that that gives us back. We'd like to show it's actually a path in ON. So here we need to know a little technology for matrix exponentials. For example, the exponential of the transpose of an exponential is the exponential of the transpose. That happens to be true. You can prove it for partial sums, and then you can take the limit. Or whatever. What's your vote? Anyway, it is true. This is e to the b transpose s. S is a scalar, so it just sits there. And then you got e to the b. Thank you, S. Yeah.
So it's e to the b transpose plus b.
Mm-hmm.
Oh, yeah.
Well, we can't do that.
Oh, right.
I can't, as much as I would love to say that it's, I mean, I would love to say that this is generally true, but I really have to stop and think about this because, see, that's one of the technical things that we're going to have to come to terms with is it's not generally the case that e to the a times e to the b is e to the a plus b. That's actually false. So this is at least questionable. Because we don't have a law of exponents for matrix exponentials. The non-commutativity spoils it. And that's what that Baker-Campbell-Hausdorff relation is all about, is it measures this departure from the usual law of exponents. But here,
Right. Now we can do it.
these matrices, they commute, right? And the point is we can, yeah. So that's e to the minus bs plus bs, e to the 0. So, bam. That still doesn't answer the question, how do you know that, how do we know that this gets, it's not, yeah. All right, so let's see here, how about another one? What if we did, let's try SLN, what would that look like? Or how about GLN? I mean, does that, what does it mean then? Can I erase?
Yeah, I guess so. I can go back and look at the video.
Oh, okay. I just bought the book today. We'll see how long it takes for it to come to you guys. But I want to make sure we do something substantive this semester. I think this book is it's more likely to steer me in the direction of telling you guys something quantitative and also you might find yourself taking a graduate course out of this elementary book later, and it would be good to have started on it. The odds are pretty good for that. It's a very popular introduction to representation theory book. A lot of schools are using it. So here, if I have a curve, right, G, which goes, say, from R to G, L, and let's work with the complexes just for kicks. And I've got gamma 0, right, is equal to what? Yeah, identity. What do I get to say? Well, I guess I have gamma of t is an element of GLN C, right? And that's true. I mean, I know the determinant of gamma of t is what? Not equal to 0. Doesn't seem very illuminating either. Let's turn the tables here. Let's look at this from a different perspective. Consider the curve. Yeah, just thinking about. I mean, think about this a little bit more here. Think about the curve, gamma of t, right, equal to e to the tx. right? Then what? Gamma prime of 0 is x. If I can show that gamma of t is in GLNC for each t, then that will show that every single possible n by n complex matrix is in the tangent space to GLNC. So how do I show that this? Well, I gotta take the determinant of it, you see. Determinant of the exponential of e to the tx. That's not bad. Remember what the determinant's defined to be. It's the sum I equals, I1 da da in equals 1 to n of epsilon I1, I2 da da in, counterposed against like A1 I1, A2 I2 da da da, right? That totally antisymmetric n-fold, and your combination of the antisymmetrized components of the columns of the matrix. And then you just got to do it for an exponential. It's not too bad. Fortunately, there is in fact an identity, which we should prove some other day. This is an amazing identity, but it's true. This is the ordinary exponential, all right? The ordinary exponential of the trace. Of tx. So the determinant of the matrix exponential is the exponential of the trace of the matrix, which is such a precious identity because it immediately tells us that this is the exponential of something, but whether that's, in principle, this could be a complex matrix, right? So this is really the matrix exponent. This is the complex exponential we're talking about here. But that's no problem because even the complex exponential is never 0. Right? Sine and cosine are never at the same time. So that's not 0. Therefore, x is, x is an element of what's called little GL, little GLNC, right, for all x in what we would call MNC, or I would call CM by n, right? A useful philosophy is this. Cn by n is just a set of n by n complex matrices. However, while this is equal as a point set to GLNC, I personally think of this one, the one on the right-hand side, even though they're equal as point sets, I think of this as a Lie algebra, okay? So it's not just Cn by n, it's Cn by n with a so-called Lie bracket structure. What's a Lie bracket? I don't know. Who knows what a Lie bracket is? We'll find that out soon, but, so this is this set of matrices plus this Lie bracket, this Lie algebra structure. And the same calculation works for so basically this is like the background. All right, so like if you can imagine, I don't even know how to picture it really, but it's like kind of like the total tangent space is the Cn by n or Rn by n. That's as big as the tangent space can possibly get for these matrix groups of n by n real or complex matrices. But usually it's something smaller like this, this closed subgroup, right, in the topological sense, the ON. What's the dimension of ON? Well, you can actually count that from the number of parameters it takes to get, you can see it from these guys, this condition, B transpose. Basically, if you think about that, the number of curves that go through the identity sort of reveal the dimension. Right? If you're dealing with an abstract manifold, and through one point on the manifold that's a generic point, you can find 3 curves that go in genuinely independent directions, and no more. Well, that's a 3-dimensional manifold. This is also true for Rn, right? If you're working in Rn and you can only find 2 independent directions, at a point, well, you're working in R2, right? If you can find 3, you're in R3. If you can find 5, but not 6, you're in R5. Same, you can think about the same kind of thinking from looking at the tangent space, the identity of the group. So, like for example, O3, then you'd have 3 by 3 antisymmetric matrix. Antisymmetric matrices have 0 on the diagonal, and it's just as many components as you have off the diagonal. So we're like 3 by 3, you'd have like A, B, C, and then minus A, minus B, minus C. So O3 is actually 3-dimensional. In contrast, O4 would be 6-dimensional, because you'd have 6 off diagonals. Okay, so then another example. How about SL? What is SL? What does SLN look like? What's the tangent space? What would like SL? I'll do it real this time. What's SLNR look like? So we'll take the viewpoint that it's the tangent space of the identity of SLNR, okay? Again, we want to come to better terms with where this matrix exponential is coming from and why that's true. But for now, we have gamma, let's see here. So gamma of what? Gamma of t is what? What's the condition? If gamma of t is an element of SL and R for all t in the reals. And this isn't really essential. You could work with plus or minus epsilon neighborhoods of 0 if you wanted to. It's just easier just to work with the domain. You can always like reparameterize the curves so that they kind of go slowly through 0 and you just make it stretch out to the reals or whatever. But how about this? What does this mean? This means what?
Determinants 1.
Okay.
I feel like tap did something like the derivative of the determinant. It's like the trace of the derivative. I don't know. It's not like
Oh, right. Yeah, tap has some really sneaky thing here.
It's 5:00 p.m.
You read tap last semester, you remember?
Well, I don't remember that.
That was later. Now, if I can cheat and say, well, that's the determinant of e to the tx, right? Then this is the exponential of the trace of tx, right? And if you differentiate this, we get trace of tx.
Times x?
I can pull, first of all, I can trace of x rather. I can pull the t out by linearity of the trace. And
times the exponential of 2 trace of x. Which means the trace of x has to be equal to 0.
right, since this is non-zero, it forces that to be 0. So in fact, getting to the point here, SLNR in fact is A and GLNR such that the trace of A is 0. That's one real equation on n squared parameters. So this is an n squared minus 1 dimensional algebra. For example, SL2 would be 3-dimensional. You'd have 4 minus 1, or SL3 would be 9 minus 1, 8-dimensional. What it is?
That makes no sense.
Which one?
The determinant equaling 1 would imply the trace.
Oh,
equaling
I'm
0.
differentiating. So differentiate this. The chain rule pulls out this, which is just a constant. And then you've got times exponential, which is still non-zero. So but on the other hand, derivative of 1 with respect to time is 0.
Well, yeah, I follow the math, but intuitively, it doesn't make much sense to me.
Ah. Well, what would suffice as intuition here? I'm not sure. I mean, we could explicitly take a traceless matrix and exponentiate it and see that, out pops a determinant one thing. I'm not sure that would be helpful.
I think we just need to understand the matrix exponential better.
That is absolutely the case, right? That is what we need to understand. So our next order of business is to just take the matrix exponential apart from front to back and try to really understand it as deeply as we can.
Well, I think if we could prove that top thing up there where the tangent space times G is equal to all of that.
Yeah, why is it tangent space at the identity?
That would help immensely.
See, what you're really saying here, right? To say so everything is happening. I mean, I can start to give you an explanation for that. The big idea is this, right? Let's keep it real for a second here. G is some kind of like subspace of GL and R, right? If I can hit, because these groups, the real groups at least, they're subgroups of GL and R. The tangent space to this is this, which is basically just, as a point set, it's n by n real matrices. Okay, so if I can find, if I can take an arbitrary, x in here, and I can say, that is equal to gamma prime of 0 for gamma of t equal to e to the tx, we work that out, then that means that this is a surjection. If you think geometrically, if this is the identity, right, then if you look at these paths which are generated from these things, they cover all possible different directions because their tangent vectors x are completely arbitrary. Now the question is, how do I know that there exists? It's a question of existence that we're asking, right? So if you look at this as a differential equation, what is it really asking? Look at this as a differential equation. You may not see that yet. So what do we have? We have d gamma dt. Right, what we're really trying to solve is d gamma dt equal to, I believe, x times gamma. And gamma of 0 is equal to the identity, and gamma prime of 0 is equal to x. This is a problem of differential equations. We have a matrix differential equation for a given x. This is a linear differential equation. And it's an initial value problem. So the existence of the solution actually is given by there's a theorem in differential equations that says if you have an initial value problem to a linear system of ODEs, there is a solution. And in fact, I already wrote it here.
And we can just check that. That wouldn't be too hard.
Yeah, once you take this as the definition of the matrix exponential, you can differentiate, and you'll show that the derivative of this is in fact x times that, which is to say that derivative of this is x times that. So it's a solution to this, and then uniquely so by the uniqueness and existence theorem of ODEs, which we have not proved, which I should prove for you guys sometime. But to do that, of course, we need to delve into the contraction mapping principle stuff and some of the harder fixed point analysis and analysis. Not really this course. So usually you just see this thing used in this course. People just like quote it, and then go from there. So to understand this, it doesn't maybe still hasn't clicked for you guys yet, right? And it won't click until we come at it from the right angle and we've read the right sections and kind of led up to it in the right way. So at the moment I'm just kind of taking all the Legos and throwing them out on the table and kind of just sorting around in them, looking for interesting pieces. I hope that's okay. Is that okay? I guess you could say it's not okay. I mean, I don't know. Then I would just give you more homework. Did you guys ever find what's that?
So then what would I do with all the Legos?
Yes, I Did you guys ever find that dreadful map I was asking you to find?
More like looked it up on Wikipedia and.
But did you understand it?
No.
I think that's a very the way that correspondence between those two things is very. I think that problem alone shows you how much is hidden in Stillwell. Right? I mean, he has found a way of talking about that without letting you in on the fact that it's quite complicated. It's very, and on the one hand, it's very, very gifted exposition, right up until the point that you ask, what is that map? Anyway. So these guys, right, will be what? By the way, in physics, all right, a little difference, like in physics, they don't tend to exponentiate just a matrix. They tend to stick a factor of I up in here for various physical reasons. And so like, I think we could do almost the same song and dance here for UN, right? What would we get? We would get what? In terms of, if we just look at e to the bt, right, as being a typical A. So almost the same calculation we did would show what? B decker plus B is equal to 0, right? And so for the mathematician who says that you exponentiate the Lie algebra like that, we would say that little un would be just like, you know, so-called skew Hermitian. This is the conjugate transpose.
Yeah, I was about to say this. So that's just the conjugate transpose.
Yeah, conjugate transpose.
Okay.
However, physicists, for various reasons, like to look at things like this, e to the IH. Something like that is the kind of thing they do. And if you assume that that is an element of UN, right, if you include this little factor of I here, what happens? Well, conjugate transpose, right? So you end up with getting like minus, you end up with like minus H dagger, you know, plus H equals to 0. In other words, if you include that extra factor of I in the exponentiation process, you get H dagger equals to H, the so-called Hermitian. And that's the other reason they like it, is because we like to talk about Hermitian operators in quantum mechanics. Hermitian operators from the spectral theorem have real eigenvalues. Those real eigenvalues correspond to real observables. And so you exponentiate a Hermitian operator in the Lie algebra, you get, you know, if you include this factor of I, you get unitary, which is a probability preserving transformation. So if you have a physical group of symmetries and you're working in physics, then you have some extra, I would say, reality conditions to deal with. You stick some factors of I here and there, and so if you try to compare what we're doing to like a physics textbook, you'll find some disagreement. But again, it's mostly because they insist on studying this thing called reality, and so, you know, pesky physicists. Don't worry, I won't talk too much about that. All right, so keep it unreal until the next class. Let's see.